Good morning, everybody, from my side. The topic is industrial biocomposites, which are vegetable oil-based, made of products from HOBUM and partners. And before I start with the presentation, I would like to mention the sponsors. The results I will show today are partially financed by the Bundesministerium für Ernährung und Landwirtschaft and governed by the Fachagentur für nachwachsende Rohstoffe. Also, part of the work is done by our partners from Fraunhofer WKI, and other partners from the industry are Greenboats, a Bremen-based bio-entrepreneur company, and also a startup from Holland or from the Netherlands, Relevant, and I will come to that in a few minutes. Why biocomposites? I will go in a little detail into that one. What applications have been realized, the partners, the performance, and the future trends. So this is a door for a sports car that's been realized in the last years, made out of flax or linen fibers. And why biocomposites? Well, first of all, we have a weight reduction compared to steel and glass. In total, we found out in an LCA study during the project that we also have a lower carbon footprint. We can make this door bisphenol free, which is also a topic of the future if we talk about epoxy. It turns out that natural fiber composites can help noise reduction. They have better insulating properties, and also it seems that in the event of an accident, the splinter behavior of natural fibers is better than compared to, for instance, carbon fiber. That brings us to the next slide. Here you see some data from tests, or not data, but pictures from tests, carbon fiber composites have been crushed, and also the natural fiber composite has been crushed, which is made in this case from linen fiber. And you can see pretty nasty splinters that come from the carbon fiber systems. And whoever has worked with carbon fibers and has seen carbon fibers breaking, these splinters really enter the skin and can make nasty injuries. So there's also good reason to maybe look at the natural fiber composites. How is it done? I will show two main ways how to apply. One is the resin transfer molding, where you have a convex and concave mold with a void, and it's a press system, so the upper layer will be pressed on the bottom layer. You put the linen fabric inside, close the two molds, and then pump the A and B mixture into the system and fill the the natural fiber product with the resin system. And if you've done it right, you will get the result on the right side. The mold has been opened here. The mold is, of course, heated to 130 degrees roughly, and then you release from the mold, and you have one part of this door, the outer part. And on the right side, you can see also the finished product, how it's been mounted to the race car. The clear coat actually is also made of a marginal 901, which is also based on natural products. So the entire making of this door led to a pretty good content of renewable materials. We reached at the design freeze, that was already some time ago, roughly 70% bio-based material. Big part, of course, comes from the flax fiber. The other industry applied and used method is the vacuum infusion. Instead of pumping inside. You apply a vacuum. You have only one mold, and you put a film on top of the fabric, and you vacuumize, and then suck in the A and B component of the resin, which is previously mixed, and then you put the whole thing in an autoclave and cure the product. And on the right side, you can see quite complicated structures are possible. This is a trunk flap of a Volkswagen Scirocco. And so these two systems are mainly used, the resin transfer molding and the vacuum infusion. Next slide brings us to our partner Greenboats. I will call them the masters of infusion, and we're pretty proud to team up with them and deliver resin systems in the future. As you can see, they are really into the material. This boat that you see here is a day sailor entirely made out of flax fiber and with Bio Composites. And they have the entire value chain. They have the yarn, the flax yarn, they have the flax fabric, and they really know how to. And what they mostly use is vacuum infusion. And it's not only for small parts, they master actually to make the entire hull of a boat that you've seen in one go with this infusion system. So this is all based on flax fiber and bio resins. And not only boats, but there are really entrepreneurs in that field. They can make monorails. They build parts for airplanes and also a lot of lifestyle products. But this is the small parts they do. They now take the next level and go to a mass production of boards that you can see here on the left picture. It's actually two plates with a kernel. It can be a honeycomb inside. It can be a foam inside. The different possibilities. And it's a modular system, so even the corner parts are made of the flax fiber, and you can realize various geometries with this modular system. So they're really ramping up in Bremen right now, building a line that will deliver a lot of this material in the near future, and we're really happy to team up with these guys over there. So what are the components that can be used other than bisphenol-based and amine-based? It's also possible to use our epoxidized linseed oil. It has an oxirane content average 8.5, and the bio-based carbon content is 100%. Of course, the oxirane rings in an ELO are less reactive than the glycidyl ethers of bisphenol A resin, but at a certain point they will react and will form a nice network. And the other component that is also quite interesting is admergenic acid that you see on the right side. It's Diels-Alder product out of an isomergenic acid, a conjugated C18,2 acid that has a Diels-Alder reaction with maleic anhydride to yield this anhydride. So it's in principle a molecule that can react with at 3 points. We have 3 acid groups that can react with the oxirane rings. So, and now there's another partner that I would like to introduce, the company, Dutch-based company Relevant, a spin-off of the university, TNO. And they really come with the hottest thing in the bio-based raw materials, 3-methylphthalic anhydride made out of renewable material. And also there is a Diels-Alder reaction included with maleic anhydride. That's the reason why the molecule in the end has 60% bio-based carbon. Why is it a remarkable molecule? If you see, phthalic anhydride is already used in the industry for many years, has a melting point of 131 degrees. 3-methylphthalic anhydride from renewable resources has a considerably lower melting point of 118. And if you mix the 3 MPa with our artemisinic acid, you have an eutectic effect, and you even lower the melting point to 106. So at 106, it's completely molten and liquid. Why is this important? If you look at the fill times that we have to fill the voids, either by infusion or resin transfer molding, it's a pretty speedy process at higher temperatures. So if you look at the green line, it's 127 degrees. You have about 30 seconds, and then the viscosity has already doubled. And you have to really hurry up to get material into the void or into the fabric. At 120 degrees, we are already at 1 minute. And at 100 degrees, that's the blue line, you have about 3 minutes, which should be sufficient to fill the entire void. So it's very important to lower the melting point in this respect. And that can be done with 3 MPa in a very nice way. Moreover, 3 MPa has a very good yields a very good glass transition temperature. This rigid molecule will really boost the glass transition temperature. So this part that you see here on the left is just made in the laboratory at the Fraunhofer Institute in Hanover. And we made it with infusion technology, and we could repeat it several times. It always works. It's a bisphenol-free system. And the bio-based carbon content of this panel, which is a part of I think, a Renault car, is at the end 85%. And the glass transition temperature is well above 100 degrees, measured with the dynamic mechanical analysis. So if we compare what can be achieved with truly bio-based materials here, if you just mix ELO with artemisinic acid, you will have a bio-based carbon content of the resin system of 91%. But the glass transition temperature you will reach, depending on catalyst and temperature that you apply and the curing, is 15 to 55. In some applications, that might even be enough. Most of the application that we're talking about, it is not enough. Of course, the composite flux fiber will then have a bio-based carbon content of 95%. If we now modify our products a little bit, and we use ELO 70, artemisinic acid, and well-known methyl hexahydrophthalic acid, anhydride, it's liquid anhydride. You lower the carbon content, of course, to about 56%. The glass transition temperature is already close to 100 with this system, depending on the temperature you use in the curing. And in the bio-based carbon content of the ready-made composite will be around 78%. If you now take the 3 MPa into the equation, you raise again the content of the resin system to 71%. And that's more important, the glass transition temperature after the curing, you can raise even above 120 degrees. That's what we have found with our measurements. Depending how you cure, the higher the temperature you cure, the better the glass transition temperature. And finally, we have reached a composite made of flex fiber, which has a bio-based carbon content of 85% and a high glass transition temperature. What the future will bring? Certainly, BPA, bisphenol A, is pretty much under discussion. So we will go away from the bisphenol A-based products. And we're focusing at the moment on algae, on fluorotannins. And there's an interesting molecule, fluoroglucinol. 50% of the fluorotannins is this monomer compound. And if you turn that into a glucidyl ether, you get extremely nice glass transition temperatures when combined with artemisinic acid or artemisinic acid 3 MPa. Also, we're looking at isosorbit diglycidyl ether based on sugar molecules. So there's a lot of things going on where we are looking at other starting materials other than just vegetable oils. And before I finish, I would like to use the opportunity to thank my buddies from the Fraunhofer Institute, Ole Hansen and Stefan Friebel. It was a pleasure to work with you the last years. Really appreciate it. Cornelia Sanders and Friedrich Daimann from Greenboats. They were always available for discussions and showed me what is possible with natural fiber composites. And Monique Wecking and Roger Blockland from the startup Relevant, who provided the precious 3 MPa for our tests. And yeah, thank you for your attention.